In this lecture, we will learn what it means linearly dependent vectors. This is a generalization of a very natural situation, very natural term. Imagine two vectors. In a general case, they go in different directions. Sometimes the two vectors may be in a single line. This is some special situation, and we say these two vectors are linearly dependent. Or if we have three vectors like that, they may go each in a separate, in a different direction. But sometimes two of them may be in a single line, or perhaps the three may be in a single plane. This is something extraordinary, something exceptional, not a typical situation, and we say these vectors are linearly dependent. To give a more precise definition of the term linearly dependent or independent vectors, let us first introduce the term linear combination. We know that given a vector, we can multiply the vector by a scalar, giving as a result a new vector, and then we can add vectors. So we can combine these two operations, and for vectors, say a1, a2, up to ak, each from a common space Rn. That means each of the vectors must have the same number of components. We can multiply, vectors should be denoted by a symbol with an arrow. We can multiply each vector by a scalar. Say we multiply the vector a1 by scalar alpha 1. We multiply the vector a2 by another scalar alpha 2, up to, and the last vector a sub k can be multiplied by a number lambda alpha sub k. And then we can add all these, giving as a result another vector from the same space, from Rn. That means having n real components. And this operation is called a linear combination of these vectors with these coefficients. Now, if all the coefficients alpha 1, alpha 2 up to alpha k is equal to 0, we say this is a trivial linear combination. Once again, trivial linear combination means that all the coefficients alpha 1, alpha 2 and so on are equal 0. Well, if all the coefficients are equal to 0, what about the result? Can we say anything about the result? Yes, if the coefficients are equal to 0, then independently of what the vectors are, the result of this linear combination is indeed equal to 0. We write a little arrow above 0 to distinguish the 0 vector from a 0 number. Say if we have if n is 3, just to give an example, then 0 with arrow would be a 3-component vector, each component being equal to 0. Well, and now a natural question arises: can a non-trivial linear combination of some vectors be equal to 0? Well, and the answer is sometimes yes, sometimes not. And if it is the case that a non-trivial linear combination is equal to 0, there must be something special with the vectors. Well, let me start with a little example. If the first vector is, say, 2, 3, and if the other vector is, say, 20, 30, that means the vector in the same line just 10 times longer. We could visualize this as 2, 3, 30 like that. Can we build a linear combination of these two that is equal to 0? Sure, we can. A trivial linear combination. Okay. Can we build a non-trivial linear combination of these two vectors equal to 0? Yes, we can. If we take the coefficients 10 and minus 1. We can write minus 1 times a2, or we can just write minus a2, that's the same. Because then we have 10 times a1 is 2030 minus a2, and this is indeed a 0 vector. So we have found a non-trivial linear combination because it is not true that all the coefficients are equal to 0, which is still equal to 0. But this is only possible if there is some special relation between the vectors. They cannot be just randomly chosen. And this special property is called that they are linearly dependent. So the definition goes this way. We say a system of vectors is linearly dependent if there exists a non-trivial linear combination equal to 0. So we say a system of vectors is linearly dependent if there exists a non-trivial linear combination equal to 0. And in the opposite case, we say the vectors are linearly independent if there is no non-trivial linear combination equal to 0, or in other words, if the linear combination of some vectors is equal to 0, and if it is only for trivial linear combination, then the vectors are linearly independent. Let's have an example for independent vectors. If we have, say, vector 1, 2, and if we have, say, vector 2, 3, then they are linearly independent. They can be sketched in a plane. 1, 2 looks like that. And 2, 3 looks like that. They go in a similar direction, but not exactly the same. If we want to find some linear combination of them, then it turns out that the only possibility is alpha must be 0, beta must be 0. Only the trivial linear combination of these two vectors is equal to 0. Okay, let's show this. So alpha times the vector A plus beta times the vector B should be 0. So this is equality between two vectors, and that means that the first component on the left must be equal to the first component on the right, and the same for the second component. So alpha plus 2 beta must be 0, and 2 alpha plus 3 beta must be equal to 0. This is a system of two algebraic linear equations for two unknowns, a homogeneous system. And this can be solved by many ways. Perhaps one very stupid approach is to express alpha in terms of beta and to substitute into the second equation, and then we have 2 alpha will be minus 4 beta plus 3 beta is 0. That means minus beta is 0. That means beta is 0, and if beta is 0, then alpha is 0. And this is the only solution of this system. So it turns out indeed that only the trivial linear combination is equal to 0, and this completes the proof that these two vectors are linearly independent. In the next section, we will see some signals, some indicators that a system of vector is linearly dependent or not.